So anyway, this kind, I've already given this away, but let's fill in the blank. This kind of sequence, an equals a sub n minus 1 plus d, I'll explain that notation in a minute, is called arithmetic. Now, where the heck did I get this? That's a generic recursive formula. Let me show you how we can figure out where that comes from. If you take a look at what we just did, it's almost the same formula except for there's a d right here where the 5 is, right? Oh, so what we're saying is instead of having a common difference of 5, we're making it generic. We're saying it's d. In this case, d equals 5. So how do we get the nth term? We take a sub n minus 1 plus d. Where d in this case is 5, but it can be whatever you want it to be. It could be negative if you want it. So that's the recursive formula. So again, in words, I've already said it, but let's go ahead and make it official. In an arithmetic sequence, each term is found by adding a common difference d to the previous term. Now, what do we want to do, if possible? With just about any recursive formula, you know, they're not necessarily hard to use unless you want the millionth term. Because then you have to find the first 999,999 terms, and then you got to find the first 999,998 terms, and then so on and so forth, if it's recursive. So what do we want instead of a recursive formula? We want an explicit formula. So we already know a trick for getting the recursive formula for any particular problem. I showed it to you in the first example, but let's see if we can come up with a generic formula. And we're going to think recursive. We often think recursively to get our explicit formula. So unless you're feeling really argumentative today, I'll bet you would agree that in any arithmetic sequence, A1 is equal to itself, right? And assuming the common difference is D, what would A2 be equal to? A1 plus D. You're not wrong, those of you that said A2 equals A2. But then we didn't get very far, right? We could keep doing A3 equals A3. But we're looking for a pattern here, right? So we want to go back and actually generate the generic terms of this sequence. So this is just a generic arithmetic sequence that we're generating the terms of, recursively speaking. So we start with A1, and to get A2, we add the common difference D to A1. Okay, so then what would A3 be? A2 plus D, but here's a trick that'll come in useful in other problems. If you can, have as few unknowns as possible. In other words, relate to what you already have, if possible, so that you have as few subscripts as possible or as few unknowns as possible. So we do know what A2 is in terms of A1 and D. So the idea here would be, could I replace A2 with A1 plus D? Yeah. So there's A2, right? And then I add in D. Are those parentheses really doing anything other than indicating the substitution I just made? No. Drop the parentheses, combine like terms. What do you have? A1 plus, this is 1D, plus another D makes 2D. We're about, if you haven't seen the pattern yet, you're about to. Okay, A4, what would A4 be? A3 plus D, but wait, we know what A3 is in terms of A1 and D. So in for A3, what could I substitute?
A1 plus 2D.
So this guy, right? So A3 would be A1 plus 2D, and then I still have this D out here, right? So drop the parentheses. They're not doing anything other than indicating the substitution I just made. And then add like terms. What do you have? A1 plus 3D. Can you predict what A5 would be without going through all this work? A1 plus 4D. Does everybody see where you got the 4 from? If you look at the coefficients of D, even starting here, you could, if you put 0 times D. How do the coefficients of D, let me use a different color here, green. How do the coefficients of D relate to the index over here in each one of these? It's 1 less, right? It's 1 less. So I think we can use that, maybe use a dot, dot, dot. Okay, so what would an be? So now the index is n, and what would the coefficient in front of d be? It'd be a1, it looks like, every time. So a1 plus something times d, right? What would that, so parentheses for something, what would that something be? N minus 1. You got it. N minus 1. And there's your generic formula for the nth term. This only works for an arithmetic sequence. So this is a nth term formula for and only for an arithmetic sequence. So for any particular problem, all you have to do is recognize what D is and recognize what A1 is, fill it in, and you've got your formula. So now you have two ways to get the nth term formula. You can use the trick I showed you above, or you can use that formula, which comes in handy in certain situations. Oh, one thing I should point out, let's go back to the example from before. You guys have seen these kind of this explicit formula for an arithmetic sequence. You've seen these kind of formulas before. Does this ring a bell? Y equals mx plus b?
Yes.
Well, here the input isn't x. It's n, right? And the output isn't y, it's an. But it doesn't matter. It's still what we call a linear equation. Now, since the inputs are only allowed to be n in the formula encircled, a sub n equals 5n minus 3, the inputs are only allowed to be natural numbers, that is. When you graph it, you only get dots. You don't connect the dots because you're not inputting any numbers between the natural numbers. But the dots would lie in a line. And the slope of that line would be 5 in this case. So, and that remains true for the general formula. So if we go down here, it's not in quite the same form, but n is still the input, n to the first power. That's how you know it's linear. If n is to the first power, if the input is to the first power, and the output an is to the first power, and there's no other variables involved, and they're not multiplied together, you couldn't multiply x and y together. It wouldn't be a linear equation anymore, or an and n. But as long as it is of this form, where n is to the first power, the output a sub n is to the first power, it's linear. And the slope in this case would actually be d. Okay, d, the common difference, is the slope, just like 5 was d in the above problem. That is the slope. So I just want you to know that this is a linear equation with respect to the input of n and the output of a sub n. D is going to be, in any particular problem, d is going to be your slope, and you'll be able to figure out, or you'll be given what that is. At the end of the WebAssign assignment for 11.2, there are some review problems for linear equations, y equals mx plus b stuff, right? So you have to know that in y equals mx plus b, that m is your slope. What does b turn out to be?
The A1.
Well, 0b is your y-intercept, right?
Yeah.
Remember that? The place where the graph crosses the y-axis if you have a solid line. And you're allowed to plug in any x value you want. Okay? So you'll be reviewing the last handful of problems. You'll be reviewing that stuff, which you've seen before in probably at least two other classes. In this example, let's find an and a10 for, the same one we had at the beginning, 2, 7, 12, 17. So I already showed you one way to do this, right? So I want to use the explicit formula we just came up as an alternative method. So an, remember, just write it down every time you use it. You'll have it memorized in no time. A1 plus n minus 1 times d. You do have to memorize it for the exam. You can forget about it after the class. But we're so bad at memorizing things now and there are certain things you need to memorize just so that you can do the problems at a reasonable speed. And then it isn't that you keep it in your brain the rest of your life. It's just that you memorize it for the relevant tests in your math class, and then if you ever need it again, it's easy to get it back in your brain. On these problems, I always find, even if it tells me to find A10 first, which it might in the homework, I always find AN first if you have to find it anyway, because then you can just plug in 10 for N to find A10. So that's the order I wrote it in, but your book may switch, or your book and your WebAssign may switch the order. I always like to find the nth term formula first. Okay, so let's fill it in. Oh, and by the way, if we just wanted A10, wouldn't it be quicker just to plug in, just to add 5 a few times? Yeah, but we want AN, so we might as well use this formula. So fill it in. What do you get for A1? 2, it's right there. It's the first one. So plug in A1. A1 is 2. And then we're going to go plus n minus 1. Now, if you didn't already know, you'd have to figure it out. What's D? 5. So if this weren't a problem we already worked, you could take perhaps 7 minus 2 to get D. And that's going to be 5. But of course, you could take 17 minus 12. Any term minus any other term, except I guess for the first term, to get D, right? Now, why doesn't this look the same as the formula we came up with at the beginning, up here? So this is the formula we came up with up here. 5n minus 3. Why doesn't this look the same? Well, would it be the same if we just manipulate it algebraically? Is it equivalent? Yeah, it'll be the same. It's just a different format, right? How could you get it to look the same as what we had above? Distribute, right? If you distribute that 5, you'll get 2 plus what? 5n minus 5. And then like terms, 2 minus 5 is 5n minus 3, which is what we got above. Okay, so it really is the same formula. Now, you can leave it. In many cases, you'll just leave it like this. A10, so you were about to tell me what to do. Sorry, and I interrupted. What were you going to say to do?
That's what I was asking, because I wasn't sure if we were...
Okay, so to find A10, where do we plug in the 10? For n. Now, you could use either formula, right? Which formula do you want to use? The second formula. So A10 would be what? 5 times 10 minus 3. What's that going to be? 47. So there's your other answer.